Good morning, and thank you for taking part of our presentation. My name is Sam. We have James, Maria Martha, and Eric. And our advisor is Dr. Kinsey Jones. Our project is implantable medical microconnectors.
So the issue with microconnectors is that it's hardwired. However, right now, millions of people worldwide are affected by neuromuscular diseases, hearing loss, and stroke. Oftentimes, the standard therapies to these diseases is painkillers, surgery, injections, and this often interacts in their day-to-day lives. So a better alternative to these therapies is a microconnector, a neurostimulator. So a neurostimulator is composed of leads as well as the actual neurostimulator device. And the problem with this is that it is hardwired. So it's the interchangeability between the devices makes it very difficult between the doctor and the patient since it's permanently attached. We're also going to minimize the size of it since it's inside the body and we want to make it less intrusive. We're also going to increase the channel count in order to increase the stimulation and for it to treat disorders such as Alzheimer's, which require more stimulation. And we're going to use biocompatible materials since it's an electrical component in a harsh environment.
Our design consists of 32 pins, which will account to 32 channels, and will be a size of 2 by 7 millimeters. The way this is going to function is pins will be on one half while the vias or holes will be on the other half, and simply they will just connect together just by folding over. We had to do a simple design due to manufacturability. The pins will be arranged in a 3 by 10 matrix plus 2 on each end, giving a total of 32 pins. We will also have to implement an O-ring design for a hermetic seal and also titanium clips to secure the two halves together. On the bottom right, you see the prototype, and on the bottom left, you see the proposed design.
So as manufacturability is such a huge concern of our project, we want to be able to make sure that our design will really work. So we have built one prototype already in the Amory lab, and the way that we do that, we take LTCC, which is low temperature coal-fired ceramic, and HTCC, or high temperature coal-fired ceramic, which the LTCC sinters at a temperature of 750 degrees centigrade. Once we take one sheet, the design is punched multiple times in the LTCC as well as the HTCC. The vias or the holes will then be filled with the silver test material, and once the vias are filled, the layers will be stacked and laminated in unilateral press using heat and pressure to laminate them together. The assembly will then be co-fired and assembled, and the final design will be using alumina and platinum materials, as these are biocompatible.
Our prototype is going to we're going to be testing the strength of the pins, go through a cycling process to ensure that they don't break, as they are only 250 mil in diameter. Once we get to the final product, we're going to test for conductivity to ensure that the current coming in is leaving the product. And then we have to go through various testing, which is the MIL standard 883, which is the military standard for microelectronic devices. There's various tests for electrical, mechanical, and environmental. And then we need to test the seal, which is test condition 1014, which is a couple tests to ensure that liquid or gas will not come in or leave our connector. The economic aspect, a sheet of LTCC costs $20. Discrete 25 layers. Our device uses 10 layers each. A sheet of HTCC is only $2.50. Graphite ink is $7 per gram. Silver ink is $1.25 per gram. And the platinum is $80 per gram. Because the platinum is so cost prohibitive, we're not using that on the prototype. Our first objective is to test for the pin strength. And our total cost for the prototype was $56, with most of it being the graphite.
Seeing as how humans all over the world are affected by all these diseases, we want to be able to make our microconnector marketable in all these places. So our first concern is to get it passed by the FDA, so it can be marketed in America, as well as EMA, a European Medicine Agency, so it can be marketed in Europe, as well as other countries around the world. As you can see, most of our materials are mined from other countries, and we are using machines in a lab which are imported from Slovenia.
Here's our project timeline. We've already begun our initial prototype. We started back in October. We're actually going to go back to the lab this week to check our prototype our second prototype to see if it is working. Once we check that, our plan is in the spring to begin manufacturing our final device, and then the testing is going to be throughout. Any questions?
I've got two questions. First question I want to ask you is, when you're designing this design, what are what are you going to take into account to ensure that, number one, the pins do not get damaged when they get connected, and secondly, that the correct contact point connects to the correct contact point on the male and female mating?
We have, as far as the testing of the pins, it's going to go through a cycling of just attaching and detaching the male and the female to ensure that the pins will stay intact. That's just our initial test. As far as the conductivity, to ensure that we have contact, we have two proposed designs. One is similar to like a AA battery, where you have a spring loaded on the one side in the holes, and then the other is a spring loaded in the. It's kind of hard to explain, but
But I mean, is the design symmetrical? Let me go there.
Yes,
Yes.
yes.
Why? Because an asymmetrical design would ensure that they can only connect it one way. This is what I'm thinking. If you come in with a symmetrical design, and you've got 32 connectors that have different logic pathways, they're going to put it together backwards.
Well, the way this functions is you have wires coming in from one side and then wires coming in the other side. So the only way they can go is on top with the wires facing outwards. So you got the bottom half with wires coming in this way, and then this, the top half wires coming out this way. So when they connect like this in one direction.
Does that answer your question?
I'm sure I could make it work
Yeah.
another way.
We're trusting
That's
you,
what I'm
sir. We're trusting
Okay, that's
you,
the
sir.
second. The second question pathway I want to throw out there is crosstalk. Are you going to take into account that you've got fine wires that are connected close to other wires, and are you going to be doing any testing to ensure that you don't have crosstalk between the wires?
we are looking at there's two different possibilities as far as connection of the wires. One, we could be developing our own lead and connecting it through a thermosonic bonding. If we attach individual wires, we'll be using a micro welder to attach. There will have to obviously be a test to ensure that there is no top crossing of the current.
Originally, when you guys started the presentation, you were talking about folding one on top of the other.
Yes.
You weren't talking about putting one on top of the other. Putting one on top of the other is very simple. Folding, okay, you have to worry about the fact that, you know, this thing is coming across like that, and the hole may not line up with the pin, which is vertical. So, are you looking at the
No,
size?
it's not going to be.
It's not going to be folding. I misspoke. Sorry about that. Won't come out public.
Any other questions? Yes.
New timeline, the testing starts before manufacturing. So before manufacturing, what kind of testing?
Testing of the prototype.
May I see like your second slide, please?
Second slide.
Yeah. You're telling me on this slide that the engineering problem is one, that it's hardwired,
Yes.
and then the other engineering problem is its minimum size? I
Yeah.
think you've got your things,
Yeah.
negatives and your positives in this stuff. It's a little confusing to the
Yes,
audience.
my apologies.
The problem is the size. We want to minimize it.
Yes, so you would want to kind of rearrange
Yeah.
your content there. And I'm going to ask an embarrassing question. Is this inside the skin, under the skin?
Yes.
So how are you going to test that?
The device, obviously it's not going to be tested inside the human body.
Thank you.
Yeah, we have to go, all these other tests are outside of the body. The mill standard 883 for the microelectronics. There is actually, and then the test condition 883 is in a lab, testing for hermeticity to make sure that no gas or fluids can get in or out of the device. And then there is a simulated body fluid test also to ensure that there is no corrosive on the material, which the materials that we're going to use, the platinum and the HTCC, has already been tested for multiple years. That's currently used in pacemakers right now. So it's been tested for many years to test before it ever goes to animal or human testing.
This sounds like a great idea. Are there commercial or labs trying to achieve this right now that are going in parallel with you?
Currently, there is not. We don't know of any device that's being designed right now. There is one device that has already got approval, but it's only a 9-pin, and it received its patent, I believe, in 2007. It's much larger than what we're proposing, and obviously limited capability, and it actually is not commercially available because there's a company in Germany who actually bought the patent and is only using it for their product.
Thank you.
Do we have any other questions?
Okay.